Hello friends, in our previous lectures we saw how we can define or describe a unit vector in a coordinate system. So this system, it could be a generalized one, it could be a well-defined one. Now when you consider a well-defined coordinate system, that is for example a Cartesian coordinate system in 3 dimensions which comprises of the principal axis x, y and z. Now the conventional way of describing the unit vectors associated with this coordinate system is the vectors that align themselves along the principal axis and of unit length. So when you have a vector that are along or that are pointing along the principal axis and of unit length, then we refer to them as the unit vectors that form the basis. Now we saw in our previous lecture there is a generalized way of arriving at this unit vector or describing this unit vectors, that is by considering a position vector in this Cartesian space. So this position vectors will be dependent on the corresponding coordinates, that is x, y and z. Now the unit vector pertaining to each of these coordinates can be derived by considering the partial derivative of this position vector to that of the corresponding axis or the corresponding coordinate, and this will yield us the vector I, which is of unit length and it is pointing along the x direction. In the same way, we will be able to describe the vector j, which is of unit length and pointing along the y direction, and the vector k, which is of unit length and pointing along the z direction. So this description of the unit vector will implicitly take care of the length associated with the system, because when we are considering this partial derivative, we are associating it with delta x, delta y and delta z, which is rather the neighboring points which is associated with, or which rather describes the neighboring point which we describe using the position vectors. And since we are considering the neighboring point in a given system, that is then scale are of the same order, so therefore this description it implicitly takes care of the length scale associated with the unit length of this basis. Now one critical advantage of describing or understanding this mode of describing the unit vectors is, or this mode of describing the basis is, it allows us to build a basis unit vectors for any coordinate system. Now if we consider, for instance, a domain of this form, and in order to study this domain, we perceive that the way of discretizing it, the way of splitting it would be of this form here. So instead of splitting it as identical square, owing to the description, owing to the nature of the domain itself, we understand that this domain can be elegantly studied or easily studied if it is split in this manner. Now for this domain which is split, which is discretized in this way, meaning in this context that discretized is rather which has a coordinate system which can be described in this manner, and the coordinate system, this kind of coordinate system will easily help us understand what is happening to this system. We need to describe the corresponding basis. If such is our case, then this type of description will help us arrive at the coordinate system for this discretization. So what essentially we are doing is we are considering a unique coordinate system for understanding this what is happening within this two-dimensional domain. And this coordinate system is much different from our conventional x, y and z, and it's also different from our spherical r, theta and phi. So the reason this coordinates we are interested in understanding this coordinate system, or we have introduced this coordinate system, is because when you split the domain in such a way, whatever is happening to the domain it becomes easy for us to describe it. Now what essentially we want to do is, for this coordinate system we want to describe the basis. Now we take the same approach. We began by considering, so we give a generic name to this coordinate system. So even though it is two-dimensional, let us consider, at least when we are treating it mathematically, let us consider it to be a three-dimensional system, and let us give the name to the coordinate system that arises from this discretization. So discretization is nothing but, in order to understand what is happening to the domain, we have split the domain into smaller pieces, and this splitting of the entire domain into smaller pieces is what we refer to as discretization. And commonly we can have a regular discretization of squares, and in this case we have a different discretization, which it could be, it is meant to be an inclined parallelogram. And this discretization, it introduces, or in order to define what is happening within this discretized domain, we need to have a coordinate system, particularly when whatever we are discussing is a vector. We need to have our own, we need to develop our own basis. So what essentially we do is, we need to, in order to develop our own basis, we need to come up with our own unit vectors. Now in order to do that, we begin by naming this coordinate system that arises from the way that we have discretized, and this coordinate system generically we refer to as Z1, Z2 and Z3. Had this been a regular mode of discretization, then the corresponding coordinate system that would arise would be Cartesian coordinate system. It will be X, Y and Z. Now, owing to the nature of the problem that we are studying, we have discretized it in a unique way, an inclined parallel, or we have discretized the system as a parallelogram, and the coordinate system that arises from this parallelogram, we have referred to it as x1 or z1, z2 and z3. Now we want to find the basis for these coordinate system that describe this coordinate system. So in order to do that, we take the same approach. So maybe I will write the name somewhere here, z1, z1, z2 and z3. Now in order to describe the coordinate system that arises out, the basis unit vectors that arises out of this coordinate system, we begin by considering a unit or a position vector for a point here. So we have considered a point, and for a point we consider a unit vector, and this, for a point we consider, or we describe a point in this space within the domain that is defined by the coordinate system z1, z2 and z3 using a position vector, and this position vector therefore is dependent on z1, z2 and z3. Now we are considering a neighboring point along this direction, and this neighboring point, if you consider, the difference between the original point and the neighboring point would be z1 plus delta z1, and the other coordinates remain the same, z2 and z3, they remain the same. Now when you want to consider the vector along this direction here, when you want to consider the vector along this direction here, so what we need to do is, we need to take the difference between the neighboring point, that is z1 plus delta z1 minus the original point. This would give us z1, this would give us the vector that is pointing, or the vector in green. So the vector in green is described by, the difference between the neighboring point, the position vector that indicates the neighboring point, the position vector that describes the original point. Now when we want to find out the unit vector associated with this vector in green, what we essentially then would end up having is, we would end up having a unit vector that provides one of the bases for our coordinate system. So what essentially we have done is, we have taken the same approach, and now the neighboring point is aligning itself along one of the coordinate axis. It's aligning itself, or the neighboring point is along z1. So what essentially then we have considered is, we have considered the difference between the position vectors that describe the neighboring point and the original point. And then what we are doing is, we are considering the ratio of this vector, this different vector, and its magnitude. So this B and its magnitude. So what essentially we are doing is, we are taking the norm of the difference vector. And when we do that, what essentially this expression translates to is, so since the difference between, the magnitude of the difference between the two vectors is delta x or delta z1, what essentially the denominator would translate to would be delta z, and this is nothing but the partial derivative of the unit vector with respect to the coordinate z1, and this is nothing but the unit vector that is pointing along the z1 direction. So it will be E Z1 vector. So this is the generalized unit vectors that is pointing along the Z1 direction. So we have considered the nomenclature for a generated coordinate system. It is Z1, Z2 and Z3, and now we have a unit vector that is pointing along the Z1 axis, and that forms the basis for the coordinate system that we have considered, this unique coordinate system that we have considered. The same operation can be extended to the same numerical operation can be extended to other coordinate systems as well. So therefore, when you consider the partial derivative of the position vector with respect to the other coordinate Z2, then the corresponding unit vector would be E2 bar. In the same way, if we consider the partial derivative of the position vector with respect to the coordinate, the third coordinate, the corresponding unit vector will be E3. So what essentially we have arrived at is, we have found a way of describing the unit vectors that forms a basis for a generic coordinate system. Again, this generic coordinate system, it does not come out of thin air, that this generic coordinate system is of a critical importance to us, because this generic coordinate system describes the way we have discretized our domain to study the problem. So depending on the problem that we study, we have to discretize or split our domain into several ways, and depending on how we split this domain, how we discretize our domain, the coordinate system that we use to describe this discretization would vary. And now when we use a coordinate system that is reflective of this discretization, then we need to have an appropriate vector basis to represent it. Now this basis is now described by using the approach that we have seen earlier. So all we need to do is introduce a position vector, take the partial derivative of it with respect to the generic coordinates that we have introduced that reflects the discretization, and thereby we are able to introduce, or we are able to describe the basis vectors, the unit vectors that form the basis of the coordinate system that is reflective of the discretization that we have performed. So if we have considered any system, be it a regular system, be it a curved system, whatever nature of the system might be, this description helps us introduce the basis. This description helps us, or this formulation helps us introduce the appropriate unit vectors into the coordinate system. Now, this is one aspect, or this helps us the relevance of considering the partial derivatives while we are considering two coordinates system. Now, when we consider the two different coordinate systems, and when we consider the inverse relationship between them, it often led us to huge expressions. For instance, if you consider a coordinate system Z1, Z2 and Z3, another generic coordinate system, when we say Z1 and Z2 and Z3, these are generic coordinate systems. They can be oriented in any manner. So therefore, that's the reason why Z is included. It means it's a generic coordinate system. Now, if we consider another generic coordinate system, Z1 prime, Z2 prime and Z3 prime, and we say that both these are inverse of one another, these coordinate systems are inverse of one another. So there are two ways of expressing it. There are two ways, we can be sure of this inverse relation in two ways. One is when you consider the coordinates of one of the system as a function of a function. So Z1, the coordinate of one of the system as a function of a function, meaning Z1 is a function of Z1 prime, Z2 prime and Z3 prime. And each of these variables are again a function of Z1, Z2 and Z3. The same way the Z2 prime is a function of Z1, Z2 and Z3, and in the same way the Z3 prime is a function of Z1, Z2 and Z3. What we end up having is, we would be able to recover rather the original coordinate Z1. So when we say there are two generic coordinate systems and they are inverse of one another, what it essentially means is, when we treat or when we consider one of the coordinates as a function of a function, we be able to recover the corresponding variables. Now, this is for one of the coordinate system pertaining to one of the coordinates pertaining to this system. So first expression is one of the coordinate pertaining to this system. Now there are two other coordinates pertaining to this system alone. So therefore, the entirety of the inverse relation is ensured only when this is also true. Z1 prime, which is a function of a function, z2 prime, which is again a function, and z3 prime, which is again a function, and this ultimately yields us the variable z2. In the same way, when we consider z3 as a function of a function, 2 prime, z3 prime, this should lead us the corresponding variable. So all these three expressions, they arise from the single coordinate system. And now when you consider the other coordinate system, since both these are inverse of one another, then the same should hold true for this coordinate system as well. Meaning, when you start off with this coordinate system, it should be possible that when you consider z1 prime as a function of z1, z2 and z3, and each of these variables z1, z2, z3 are correspondingly subsequently the function of z1 prime, z2 prime and z3 prime. The same way z2 is a function of z1 prime. So if I write it separately, so this is a function of z1 prime, z2 prime, z3 prime, and z2 is also a function of z1 prime, z2 prime and z3 prime. z3 is also a function of z1 prime, z2 prime and z3 prime. Then I should be able to recover the corresponding variable, that is z1 prime. So this coordinate system, it yields me three relations. This coordinate system then correspondingly would yield me three other relations, wherein we start off with z1 prime and end up with z1 prime as a function of a function and end up with z1 prime as a variable, z2 prime as a function of a function, and end up with the corresponding variable, z3 prime again as a function of a function, and end up with the corresponding variable. So we need to ensure all these three different expressions are satisfied in order to say that both these coordinate systems are inverse of one another. In addition to that, if you consider the partial derivatives of each of these relations, meaning the partial derivative of z1 with respect to the partial derivative of z1, which is a function of a function with respect to the corresponding variable, then we need to consider this expression includes z1, z1 prime and z1 prime by z1 and so on and so forth, will end up with z3, or rather z1, z3 prime, z3 prime by z1 is which will be equal to 1, and this expression here alone, this expression, the first term here alone, the first term here, this expression, this first term or this equation here will yield the partial derivative which will be equal to 1, and this is the partial derivative of z1 with respect to z1, partial derivative of z1 with respect to z1. Now it is possible for us to estimate the partial derivative of z1 with respect to z2. So this is z1, which is again a function of a function with respect to z2. Now in order to do that, then we have to consider similar expression, only that this term will be replaced by, so all these will remain the same, z1, z1 prime, z1 prime and z2. So what will change is this term will change into z2 and all the rest will be remaining the same, and this will lead to a rate tensor which is 0. So what essentially we mean is this one equation alone will yield us three separate expressions that will contribute to the partial derivative of each of these coordinate systems. So what essentially we mean is, the reason we have considered all this is because when you consider just two coordinate systems, and when you want to claim that both these coordinate systems are inverse of one another, then initially we need to express it, we need to ensure that these 6 different equations are retrievable. So we are able to recover these 6 different equations. So that is the first condition. Secondly, what we need to do is we need to consider the partial derivative of these coordinate systems, And when you consider partial derivative of this coordinate system for each of these three set of expressions for beginning with one coordinate system, we will end up having 9 partial derivatives, 9 PDEs. In the same way, if you consider these 3, then you will end up with 9 more PDEs. So essentially what we end up having is, to express rather, or to claim that two coordinate systems are inverse of each other, we need to consider rather such nasty expressions, that such rather complicated way of representing these relations, these inverse relation and their partial derivatives. So we will start off with, we need to recover 6 different equations, and also we need to show that these partial derivatives, we need to rather express these partial derivatives which will amount to 9 different partial derivatives for one coordinate system. Now what we will attempt to do in this lecture is, we will try to see if there is any way of simplifying these partial derivatives, because these are hugely relevant. These are not some random partial derivatives, because these are hugely relevant. These are partial derivatives that help us recover the identity matrix. So this partial derivative, it helps us recover the identity matrix, the one that we have considered thus far. When you consider all the 9 different partial derivatives, the expression involving PDEs, we will be able to recover the identity matrix. Only then we will be able to recover the identity matrix. In the same way, these indicate the inverse nature of the coordinate system. So it is these, even though these are complicated, these are vital for us to establish the relation between the coordinate system. The PDEs, they establish the inverse relation, they help us recover the identity matrix, or they help us arrive at the identity matrix that talk about the inverse relation between the Jacobian or the partial derivative. The first set of expression, these 3 expressions, they claim, or they are the first indication of the inverse relationship between the two coordinate system. So because these are complicated expressions, these are huge complicated expressions, we cannot ignore it. They play a vital role in establishing relationship between two coordinate system. So therefore what we need to do is, we cannot ignore it. So therefore the only alternate possible for us is to find a way to handle it in an elegant manner. Instead of having all the 3 coordinate system and all the 3 dependent coordinate system put together in a single expression, we need to find out an elegant way of representing it, and that is what we will try to do in this lecture. Now when you consider the expression, or when you consider this function here, that is z1 is a function of z1 prime, z2 prime, z3 prime, and these are individually a function of z1, z2, z3, z1, z2 and z3, z1, z2 and z3. What essentially can be done is, it is possible for us to represent these variables, that is z1, z2 and z3, these variables, or the z prime variables, in such a way that only one parameter or only one term can represent all these 3 coordinates. So it is possible for us to consider a representation in such a way that only one term represents all these 3 coordinates that describe a system. For instance, it is possible for us to represent the z1, or rather z1, z2, z3 as zi, in such a way that depending on what value the I assumes, it will correspond to the associated coordinate. So it is possible for us to represent z1, z2, z3 as zi, depending on what value the I assumes, the z will indicate the corresponding coordinates of a system. The same can be extended for z1 prime, z2 prime and z3 prime. So z1 prime, z2 prime and z3 prime, and the corresponding variable to indicate the coordinates of these z1 prime, z2 prime and z3 prime can be zi prime, and again depending on the value the I prime assumes, so I prime assumes the z will represent the corresponding coordinates of the system. So this fancy z will represent the corresponding coordinate of the system. So then one way of representing this expression here, so this entire expression here, one way of representing it would be, so this expression here would be z1 as a function of z1 prime, z2 prime and z3 prime, and each of these prime coordinates are subsequently a function of z1, z2 and z3. So this expression, it recovers z1 as a variable. So this expression, now this expression in addition to this expression here along with z2 as a function of a function that will recover z2, z3 as a function of a function that will recover z3 can be expressed as zi as a function of zi prime, which is subsequently a function of zi, and this will lead me to the zi independent variable. So what essentially we have done is we have considered three different representations or three different expressions that indicate the inverse relationship between z1, z2 and z3 coordinate system and z1 prime, z2 prime and z3 prime coordinate system. And this expression, we just considered a different way of representing it by introducing an index I, and this index I has allowed us to represent these three expressions using a just a single expression. So what essentially we have done is we have just introduced a single index, and using that single index we have now represented three different expressions, three different huge expressions that indicate the inverse relation between the two coordinate system using just a single relation. So what essentially we did is we introduced an index, and this index rather can be employed to represent the coordinate systems. So when we use, in this case, this index is used to represent z1, z2 and z3 coordinate system, and in this case this index I prime is used to represent z1 prime, z2 prime and z3 prime coordinate system. Now what essentially we have done is, using this index representation, what essentially we have done is we have represented all these three different expressions using a single expression here. So now when we are treating this particular coordinate systems that are represented by the index as a variable, the convention is these variables are rather ignored when they are treated within as a, or when these coordinate systems are treated as a variable. Let me repeat. What essentially we have done is we have represented the zi. So the zi represents a coordinate system, zi prime represents a coordinate system. Zi prime represents this coordinate system, and zi represents this coordinate system, and this zi prime represents this coordinate system here. Now this here, this system or this representation of the coordinate system, in this case it is a variable, and this representation here is also a variable. So zi prime represents a coordinate system and zi represents a coordinate system, but within the brackets they represent a variable. So when the representation of a coordinate system assumes a position of a variable, what conventionally is being done is the index I is rather overlooked. So therefore the conventional way of writing this would be zi as a function of the coordinate system z, and the prime coordinates, or rather the function of the prime coordinate system z prime, and the original coordinate system z will be equal to zi. So what essentially we have is, we have represented the three relations that indicates the three expression that indicates the inverse relation between the coordinate system, and these three we have tried to express it using a single formulation, and for that we have introduced the index. Now when you introduce the index, it is possible for us to translate the three different relations into three. It is possible for us to represent the three different relations into a single expression here, and what essentially for this single expression, depending on what the value of I is, you will be able to establish the three different, you will be able to recover the three different relations. Now what we have done is, we have between these two steps, what essentially we have done is, we have fine-tuned the way of representing or way of writing this expression. That is, when the expression, when the representation of the coordinate system is in the variable position, we have removed the index I, so therefore the prime remains and the representation remains within the bracket. So when the coordinate system assumes a role of a variable within the bracket, then the index is removed. So we have arrived at a way of representing the three different conventional relations that indicate the inverse relation between the two different coordinate systems using a single expression. And depending on the value of I, if value of I is 1, we will be able to arrive at a single expression, a single relation. If it is 2, a different expression. If it is 3, another different expression. So from this one expression, we will be able to arrive at three different expressions that indicates, so depending on I1, depending on I is 2, depending on I is 3, and the same goes for I prime as well. So depending on the values of I prime, we will be able to recover the three relations that indicate how one coordinate system is related to the inverse relation between the two coordinate systems. Three expressions that indicates the inverse relation between the coordinate system. The same can be extended for the prime coordinates as well. So when you consider the expression associated with z1 prime as the function of z1 prime as the function of z1, which is a function of z1 prime, z2 prime and z3 prime, and z2, which is again a function, z3, which is again a function, and that we recover from that we recover z1 prime. When we extend the same expressions to z2 prime and z3 prime, these three can be expressed in this manner. And what essentially we have is, using the same form of a representation, we have represented the inverse relation beginning with the prime coordinates. So rather, just by introducing one index, we were able to simplify 6 different relations into a set of two expressions, and these set of two expressions then they indicate the inverse relation between the coordinate system. Now let us take the same approach, and let us see if it is possible for us to rather express in a simplified manner the partial derivative associated with each of these relations. So again, let us start with the expression z1, which is the function of z1 prime, which is again the function of z1, z2 and z3. The z2 prime is a function of z1, z2 and z3. The z3 prime, which is a function of z1, z2 and z3. Now this is equal to the z1 variable. Now let us consider the partial derivative of the z1 as a function with respect to the corresponding variable z1. Now when we do that using chain rule, what we end up having is z partial derivative of z1 with respect to z1 prime, and the partial derivative of z1 prime with respect to z1, plus the partial derivative of z1 with respect to z2 prime, and the partial derivative of z2 prime with respect to z1, the partial derivative of z1 with respect to z3 prime, and the partial derivative of z3 prime with respect to z1. This will be equal to 1. Now we have already introduced an index for I and I prime that will vary between 1, 2 and 3. So what essentially can be done is, we can write this expression in rather using a summation where the I varies from 1 to 3, and the entire expression can be written as partial derivative of zi with respect to zi prime, and the partial derivative of the zi prime with respect to zi, and this will be equal to 1. So what essentially we have done is, we have introduced an index, and using that index we have already simplified the expression that indicated the inverse relation between the coordinates. Now using the same index, we have simplified the partial derivative associated with one of the coordinates of the coordinate system. So this partial derivative, it comprises of 3 different terms, and using the indices, using the index I and I prime, we have reduced this partial derivative the partial derivative that comprises of three different terms into one term. Now this is something that you might all be familiar with. Now the thing is, when you have an identical index at the bottom and the top of the expression, you have an expression and you have the similar index at the bottom and the top, what can be done is, according to the conventions, the convention that we saw earlier, according to that convention, the summation sign can be removed. The summation sign can be removed. Again, when you have an expression and in that expression the bottom and the top indices are the same, the index at the bottom, the index at the top are the same, the summation sign that precedes it can be removed, and this convention is referred to as the Einstein's summation or Einstein's convention for summation. So according to Einstein's summation for convention, or convention for summation rather, when you have an index, identical index at the top or the bottom and top of your expression, then the summation can be removed. So what it essentially means is, when I say the I, it varies from 1 to 3, and when I have an expression of this sort, I prime, sigma I, this is equivalent to just getting rid of the summation and expressing it as this, which is nothing but using the Einstein's convention. So whenever you come across this word Einstein's convention or Einstein's summation, what it means is, this expression means there is a change, there is a summation that precedes. So whenever you see within the framework of Einstein's convention, whenever you see there is a repetitive index at the bottom and top of the term, so there is an identical index at the, so we have identical index at the bottom and the top, not top and bottom but bottom and the top. Whenever we have such a representation, whenever we see such an indication of the indices having, assuming being identical at the bottom and at the top, then, and when explicitly when Einstein convention is stated, then what it essentially means is, it means that we need to consider the summation of I. So we need to consider the summations of the items that we have here. So essentially what we have is, in this case, we need to consider the summation of I. Now, when you consider this, essentially is rather, in this case what we have is, this here is 1 and we are considering the partial derivative of the I. The indices is rather only associated with the bottom and the top term. The indices, the generic indices, are only associated with the top and the bottom and the top term. So the rest of the indices are rather the constant one, they have the value of 1. So these are not rather I, these are not rather the generic indices, these are not rather a variable, but these are 1. So what essentially we have is, we have now arrived at an expression, we have written down an expression for the partial derivative of z1 with respect to the z1 as a function and z1 as a variable. Now it is possible for us to write a partial derivative of z1 with respect to the partial derivative of z2. So what essentially then we can do is, we can write a partial derivative of z1 with respect to the partial derivative of z2. In the same way, it is possible for us to write the partial derivative of z1 with respect to the partial derivative of z3. The partial derivative of z2 with respect to z1, the partial derivative of z2 with respect to z2, the partial derivative of z2 with respect to z3, and so on and so forth. So this is just the partial derivative of one coordinate with respect to another coordinate, and if we extend it, we will be able to arrive at all these different partial derivatives starting with one coordinate system. So what essentially we have is, here we have the indices that form the bottom and top of our expression for the partial derivative, and here we have indices that are specific but they cannot, or that are not the part of the summation. When you consider the summation, only these indices vary, and the rest are rather the constant values. So using this Einstein summation, then we have to express the partial derivative of 1 with respect to 2. Then the corresponding expression would be partial derivatives of z1 with respect to I prime and I prime to z2. This would be equal to 0. So when you consider in this expression, from this expression here, if you consider the partial derivative of z1 with respect to z2, then the term on the right hand side would turn to 0. So that is essentially what we have written here. So what we have done is the indices that assume the value of 1 and 1 earlier, now they assume the value of 1 and 2, and the indices I prime that are in the bottom and the top. So it means there is a summation involved, and the reason we have not included it here because we are considering Einstein's convention. So because of the Einstein's convention, we have gotten ourselves rid of the summation. But now what we have done is we have represented the partial derivative of z1 with respect to z2 using the Einstein summation, and this is equal to 0. Again, the partial derivative of z1 with respect to z2, it essentially comprises of 3 different terms, and using some Einstein summation we have represented it in this manner, and rather it in a simplistic manner. Now when you consider the partial derivative of z1 with respect to z3 using the Einstein convention, it will be of this form: I prime by z3, and this will be equal to 0. So what we need to look, when you look closely, or what we need to observe is these indices are rather, they indicate the summation, while these indices are rather specific. So for each of these indices we need separate equations, but these indices, the I prime indices in this expression, in this set of expression, these indices, they indicate summation, whereas these indices, they are constant and they have a unique expression. They demand a unique expression. So these are the characteristic features of the expression. So the one in the blues are the characteristic features of the, in this case they are the characteristic features of the expression, that is partial derivatives of z1 with respect to the partial derivative of z1. Here the partial derivatives of z1 with respect to the partial derivatives of z2. The characteristic feature of this partial derivative is indicated by the indices in the red, whereas the indices in the black, they indicate, or they represent rather, the summation. So the indices in the black, they indicate the summation, whereas the indices in the red, they indicate a separate, they demand a separate expression. However, the values assumed by these indices, both these indices, they range from 1, 2 and 3. Both I and I prime, both these indices, they assume the value between 1 and 3, and again the indices in the red, they demand separate expression, whereas the indices highlighted in black, the encircled in black, they indicate the summation. Now what I have is, we have 3 different expression for partial derivatives, and only factor that changes is the indices in the red. Now it is possible for us to replace, similar to I prime, it is possible for us to replace these indices in red with a variable, provided we are able to understand the difference between the indices in the red and the indices in the black. So if we are able to understand the difference of the indices based on the position, then even the indices in the red can be replaced by a variable. So again, if you consider this expression here, that is, so far we have considered 3 partial expressions of 3 PDEs. So when you consider partial derivative of z1 with respect to z2, according to the Einstein's convention, this can be written as z1 by z1 prime or zi prime, and partial derivatives zi prime by z1. So zi prime at the bottom and at the top. The second expression z1 with respect to z2, again under Einstein's convention, this would be zi prime by z2. The same way the third expression Z3, this would be Z1, Zi prime, Zi prime by partial derivative Z3. Now, again, when we are able to distinguish, rather, these indices that demand separate expression, that vary with the expression, with each of these expression, from that of these indices that just indicate the summation, then we will be able to represent all these three different terms using a single expression. So all these three different relations can be represented using a single expression if we are able to differentiate the indices in the blue that represent the summation from the indices in the red that demand a separate expression. So in order to see the difference, let us compare all these three expressions. In all these three expressions, the I prime remains the same. The variable, the index that represents the summation, it remains the same. However, the index in the red, it varies with the PDE. So here it is 1, 1. It is here in this case it is 1, 2. Here in this case it is 1, 3. So when we want to have a generalized expression that represents these partial derivative, the ideal way of representing it would be, so we want to represent all these three expressions using a single relation, and that would be sigma I dou Zi by dou Zj, which would be dou Zi by dou Zi prime and dou Zi prime by dou Zj. Now this j, so again this is in the using the Einstein's convention. So what essentially we have is the I and j, they can be equal or they cannot, or they can be different. So what essentially we have done is, using this single expression, we have represented these three PDEs, and this is under Einstein's summation. So Einstein's convention, meaning the nature of these indices, they indicate summation. And secondly, so when you consider identical indices at the bottom and the top, what it means according to the Einstein's convention is summation. And secondly, we have represented the other indices using I and j, not just I alone, but I and j, to show that the I, the same, that these indices, that is the ones in the red, they can be identical, they can also be different. So in order to indicate that, we have included two different indices, that is I and j. So what essentially then we have done is, we have considered a set of three PDEs and represented it using a single expression, and it is possible for us to do that is because we were able to differentiate these indices. We were able to differentiate these two indices, the y indices in the blue, from that of the indices in the red. And the indices in the red can be identical or they cannot be identical. They may not be identical. They may be identical or they may not be identical. However, the indices in the blue, they indicate the summations. So the indices in the red, they demand separate expressions, and they may be identical, they may not be identical. And the indices in the blue, they just indicate the summations within a given expression. So once we are able to distinguish the nature of these two indices, then we will be able to represent. So we have shown that it is possible for us to represent these three different PDEs using a single relation. So we have simplified all these using a single relation. Now, owing to the different nature of these indices, the indices in the blue, the indices that indicate summation, the indices in the blue, the ones that indicate summation, are referred to as the dummy indices, or these are referred to as dummy indices because the only role that they play is rather the only indication or only representation that they make is rather the summation. So therefore these are expressed as the dummy indices. And the ones in the red that demand a separate expression, so whatever be the combination of the value the red assumes, the red indices assume, they demand a separate expression. These are referred to as the live or free indices. So we have the free indices or live indices, and we have dummy indices. The dummy indices, they rather are there to indicate the summation within the Einstein's convention, whereas the free indices, they demand a separate set of expressions. And another name for these dummy indices are the silent indices and contracted indices. So, to sum it all up again, we have some different partial PDEs in order to describe the inverse relations between two coordinate systems. And these PDEs can be represented in a simplistic way, in an elegant way, by introducing indices. And when you write down these PDEs, it is possible that there are indices that assume that are identical for a given term. These indices are identical for a given term, and these indices can be thus used to have represent the summation. So there are indices that are identical and that are used to represent the summation. And when you use Einstein convention, we can remove the summation part and just include the identical indices to indicate the summation. So when you consider Einstein's convention, when you have identical indices at the bottom and the top, so it indicates summation. Now there are other set of indices within the representation of the PDE which may be identical, which may not be identical, and these indices, depending on the value these indices assume, separate expression needs to be included to describe the expressions. So therefore, these are rather the governing indices, and these are referred to as the free indices, and the indices that just indicate the summation are referred to as the dummy, silent or contracted indices. So what essentially we have thus seen is, we have just got ourselves exposed to or introduced to the vector notation. We will build on this in the subsequent lecture. Goodbye.